Good late afternoon. My name is Sarah Hinkel, I was already introduced. Thanks a lot. I'm working at the Power Sharing Institute in Switzerland, and today I want to talk about temperature and loading rate effects on the local criteria for cleavage structure on a specific steel Eurofer 97. In my talk, I first want to give you an idea what is the motivation and what it has to do with radiation effects. Then I will talk about the local approach I used. I will introduce the material, followed by the finite element models we used and the results, and by the end I'm trying to sum it up. So let's start. My work, or my research, is actually located in fusion physics. And there we want to investigate the effect of irradiation on the material properties as well on fractional properties. Because in fusion, but as well as in fission, we are facing the same problem that we need to actually develop new small specimen test techniques. Because to perform the irradiation can be tedious because of several restrictions. The irradiation volume is limited, that's the first problem. Another problem is that you actually want to minimize the irradiation gradient within your material because you want to test at a unique condition, not at an average one. Another problem would be the handling of active specimens, so as smaller as better, and of course the available material. So here on the right hand side you can see actually some sizes of compact tension specimen, where these two are actually the specimen which were invented for radiation. But of course we have to deal with a loss of constraint. And let me first talk a little bit about what is actually happening when you irradiate material. In terms of the ductile to brittle transition curve, if you irradiate it, your material actually is going to be shifted quite a lot to higher temperatures, so it causes embrittlement. And this is due to, in fusion, the material is going to be irradiated by neutrons. And those neutrons actually displace the atoms from their initial lattice position and create so-called Frank-Capel effects. They consist of a vacancy and an interstitial. Most of these defects actually are going to annihilate, but not all of them. So they will create interstitial clusters and vacancy clusters. And after a certain time, they will form vacancy loops or interstitial loops. So, and these are creating defects. And this has, of course, an impact on the mechanical properties. If you have a look here on the right-hand side, it's representing actually a glide plane. And to move its location through this glide plane, it takes actually a certain stress. If you approach a defect, the dislocation will be pinned at this defect and it's going to bow out, and you have to increase the stress until you reach a critical angle. Then the dislocation is free to move again and your material actually yielded. So this will increase. So if the volume density of defects increases, which is the case for irradiation, you will increase the yield stress, and this has an impact onto the ductile to brittle transition temperature. For the local approach, actually several approaches have been proposed by different people, but they all have the same idea, that they actually want to account for the specimen size effect on the measured fracture toughness. In this work, I actually just wanted we are actually using the approach by Odette, which has the following cleavage criterion, that they say a certain critical stress has to encompass a certain critical area ahead of the crack tip, as it's sketched over here. And of course, in 3D, we would have a critical volume. And one interpretation of the critical stress is in terms of the Griffith stress from a penny-shaped crack with the critical radius of RC, and where gamma S is the surface energy
and WB is actually half of the plastic work per unit area to propagate a crack. And yeah, here I just want to say again that we actually want to investigate on this local approach the loading rate effects as well as the temperature on this approach in the lower part of the ductile to brittle transition region. The investigated material is actually Euro-497. It's supposed to be used in a future fusion reactor as a structural material and consists of a martensitic structure. The prior austenite grain size is in the range of about 10 micron. Those elastic properties actually we got it from literature, so they were not determined by us, but we actually determined plastic properties by using standard round-shaped specimen with a diameter of 5 millimeters, and in a temperature region of -50 up to liquid nitrogen. And for each temperature, we actually conducted tests at 3 different strain rates to account also for the strain rate effect. So let me come to our first finite element model, which was realized in the commercial software Abacus, where we first built a compact tension specimen in 3D, which has the model size of 0.18 T. The chosen crack tip radius is 0.1 micrometer, which is in accordance to experimental investigation on our pre-cracked CT specimen by fatigue. The material model is a simple elastic one, where we use these 4 different temperatures, and for the 3D model, we actually just used as an input the strain rate at the lowest strain rate. I will justify this on the next slide, why we just chose this one. One reason is the computational cost. And the stress intensity was actually calculated by the load versus displacement curve using this standard equation. So here we can see the first results. Let me just show you here on the right hand side, where I can see the stress intensity versus the temperature. The black line is indicating the lower bound for the 0.18 T specimen, and those stars are actually indicating the positions at these certain temperatures where we extracted the information from the finite element model. For the strain rate to justify that we used, we would have to have a look over here. This is actually the stress and strain head of the crack tip in the middle of the specimen. What we can be seen here is that at the peak stress, actually, the strain is in the range of, roughly speaking, 0.1 and 0.01. Usually it takes about 60 seconds to load a 0.18 T specimen up to the lower bound to fail. And if you calculate, you receive a strain rate in the range of 10 to the minus 4, 10 to the minus 5. So roughly speaking, we are in a quite good range. What we can see also here is that the height of the peak is actually decreasing and the width is increasing with increasing temperatures. What we also have done is actually we determine the critical volume at certain critical stresses at different temperature corresponding to the critical stress intensity factors. And actually what we found more or less a unique crossover. So we were able to determine the critical values, which is supposed to be at 2050 MPa. If we have a look again once more on the stress ahead, the crack tip, it seems to be that the stress has, at the lowest temperature we investigated, it has to act at least over a width of the one prior austenite grain size. So as a next point, we wanted to investigate the strain rate effect, and we built actually a 2D model because it's a way lower computational cost just to investigate if there is any effect. The crack tip radius was chosen to the same size. It was again an elastic plastic material model, with the difference that we actually inserted now the strain rate sensitivity of the stress. Means like for every temperature we inserted the 3 curves, And Abacus is actually interpolating between those three curves. And the loading, which is in mode 1, obviously was realized with these small-scale yielding equations with a t stress equal to 0. And the model, or the small-scale yielding model, actually we chose also a loading time of about 60 seconds to be able to compare things. If you look here on this stress versus stress ahead of the tractive, you can actually see the black curve is from the 3D model, and the other two curves are from the small scale yielding model, where without a response to the strain rate sensitivity, without means like strain rate was not considered, and with means strain rate was considered. So what you can see actually is that if the strain rate is not considered, and we just compare the 2D model with the 3D, we see that because we use the T-stress of 0, that the positive T-stress in the CT specimen is actually elevating the stress ahead of the tractive. And if we compare now the two small-scale yielding models, where we consider strain rate and not, we can see actually that there is a difference within the strain volume, which can be not neglected, and it's actually increasing with temperature. So let me try to sum it up. What we have found so far is that we built those 3D model with a 4.18T specimen, and we determined actually some critical values where we assume that those values are temperature independent in the range we investigated. Also, we found out actually that the critical stress has to act at least over a distance of about 1 per hour austenite grain size. For the 2D model, we see that this positive T-stress is elevating the tractive stress, and also that the stress volume is quite sensitive to the loading rate. But in fact, it's known from literature that the critical stress is actually temperature dependent, so it requires further development. And what is more important, that if you want to calibrate the critical volume for a certain material, we have to know which strain rate we consider. So if you want to compare results, we should know at which strain rate we are going to determine those values. So I would like to thank you for your attention, and I would be open now for some questions.